In this video, I'll be going over the week 3 tutorial in Trends in Computational Linguistics course. This tutorial mainly focuses on natural language generation, generating natural language text using GPT-2 model. Uh, we would be doing the following. We would get to know the background of a GPT-2 model, and we'll try to train a toy version of a GPT-2 model from scratch using ELP dataset, which contains a lot of reviews. And we'll be exploring a bunch of decoding techniques to generate natural language text, which is interesting and reasonable. This notebook was mostly tested on this specific version of Transformers library. This notebook may or might not work if you try to install the latest version of Transformers. So if you don't want to take a chance, you can just go ahead with this particular version of Transformers library. And yeah, and I would recommend you to run this notebook in your local machine using Jupyter notebook, not using Colab. I got queued out of memory error when I tried to run this notebook in Colab. Yeah, and these are some references which you can look at. The original reference for GPT-2, which was actually a successor of GPT-1, and there are a couple of other works which are related to the decoding techniques that we would cover in this tutorial. So before we start with the main content for this tutorial, let's try to do a quick recap of what we did last week. So Chiyu took a tour uh, towards understanding BERT model. So BERT is one of the state-of-the-art language representation model, and this seems to be a strong baseline model for most NLP tasks, which deals with representing a piece of text. It could be a sentence, or it could be a pair of sentence, or it could be a document, or anything. But would help you in solving natural language understanding tasks like question answering, NLI, and text classification, and so on. So the underlying model uh, in BERT is the transformer model, the blue circles that you see in this picture. And The model is trained on unlabeled text using a couple of pre-training objectives. One is mass language modeling, another is next sentence prediction. And the important thing to note in this architecture is that each node, each hidden state uh, in the BERT model is conditioned on both the left as well as the right context. So BERT, as the name suggests, tries to learn bidirectional representation at each layer, and tries to achieve the pre-training task successfully. And once it achieves the pre-training task, we can use the BERT model to solve our own favorite NLP task like text classification, question answering, or something. Yeah, so this is what we have covered in the last week. We tried to train BERT model, and we tried to solve one particular text classification task using BERT model, and it went well. Yeah. And today we are going to see another language model, which is called GPT-2 Generative Pre-training version 2.0. So this model is the current state-of-the-art model for natural language generation, where the set where you typically want to uh, uh, generate text, which is grammatically correct, which is using long-term context, and which is also using world knowledge and so on. Right. So one particular application could be building chatbots. Right. We can try to build interesting chatbots. Uh, yeah, as is one use case. Yeah. So, like BERT model, GPT-2 is also based on transformer architecture, uh, and it uses a single pre-training objective, which is a language modeling objective, a very standard language modeling objective, where we try to predict a word given the previous words from the text sequence. So this is the model architecture diagram for GPT-2. So we have the input, let's say this is the input. UBC's Master of Data Science program is a credential to set you apart. So what we are trying to do here is we are trying to feed the entire sentence here, UBC's Master of Data Science, till the end, and you try to predict at each time step the next word. So for UBCs, I try to predict the next word, which is master, and for master, I try to predict the next word off, and you do it till the end of this particular sequence. If you notice in the transformer architecture, each hidden state is dependent only on the left context, right? So for example, the hidden state for before predicting the word off, this one depends on the previous layer's hidden state from the current word, of course, and the previous word only. It doesn't look at the hidden state from the future tokens. So this is the crucial difference between the architecture underlying GPT-2 and the one that we have seen last week uh, in BERT, right? In BERT, if you see, each hidden state depends on both the left and the right context. So it sort of learns bidirectional representation. On the other hand, GPT-2 learns unidirectional representation. It's a left to right model, which is the traditional language modeling objective also. So the objective used by BERT is a more specialized objective to learn bidirectional representation. So yeah, this is what is the crucial difference between BERT and GPT-2. And another crucial difference is BERT is typically used to solve natural language understanding tasks like question answering, natural language inference, text classification, and so on. While GPT-2 model, which is also a language model, which is trained once, and we typically use it to generate some text. So we try to feed, let's say, starting few lines from a news article and try to see if we can generate the rest of the news article, right? So these are some natural language generation applications, which are interesting to us. And GPT-2 model, the original model, is pre-trained on web text, which was collected by OpenAI. It contains huge amounts of web pages. Um, so that's a large data set, and this model is also very large, and we can't really afford to train this model on our own. So we will try to change the data set from web text to ELP data set. ELP data set contains a lot of reviews written in ELP, and we will just try to sample very few reviews from ELP data set and try to train our GPT-2 model, just to show the flow of training the GPT-2 model. Yeah, but in practice, if you want to train GPT-2 on corpus like web text, which has tons of content, uh, that would be hard, and you need more resources, and you need more optimization in your code. So we are not really getting there. Yeah. So that's the context in which we are going to go forward in the first half of this tutorial, where we are going to focus on trying to train a GPT-2 model from scratch on a very toyish corpus. So that's the first part of this tutorial. And the second part of this tutorial is all about using the trained GPT-2 model to generate some interesting text. So we won't be using the GPT-2 model that we have trained in this tutorial because it's very toyish. So we would be using the pre-trained GPT-2 model given by the original authors to generate natural language text. So we would feed some sample text to the pre-trained model and try to see what the model outputs. So this is one of the most famous example for GPT-2 generated text. So if you see, you have two rows in this figure. The first row contains a piece of text which we can call it as seed text or prompt. It's written by a human, and we feed this prompt to the model, GPT-2 model, which is trained, and we try to see what it generates from there, right? We want it to generate probably the rest of the text, which should be consistent and coherent with our input to the model, right? So let's look at the input that we are giving to GPT-2 model. It says there has been some shocking finding, and some scientists have discovered a species called unicorns, and they seem to be speaking perfect English. Yeah, and the rest of the body is generated by GPT-2. We'll see later on how we exactly generate this piece of text. Let's try to look at the generation to get a feel of what GPT-2 can do, right? So it sorts of continues from where we have left. Spoke of a perfect English. It says the scientists named the population after something, and there has been some mystery, and GPT-2 has invented a scientist called George Perez. Seems to be a evolutionary biologist from some university. It's using some world knowledge, as you can see, and it keeps referring to the same scientist in the subsequent sentences. And it also knows that Perez is not doing alone. He has fellow scientists, uh, and yeah, they were really astonished to see this bird. And they discovered here that the creatures actually spoke a fairly regular English, so it hasn't forgotten that we prompted it with something related to perfect English. And it goes on and on. So yeah, it talks about South America, Argentina. So it knows that Argentina is in South America. The model is knowing some sort of world knowledge, and yeah. So yeah. So overall, what we can see from this result is that the resulting text seems to be mostly coherent with what we have prompted the model with, and it's mostly grammatical. I hardly could see any mistakes here. Probably a native speaker can find more uh, and find something or more. And it sort of uses long-term context. So it sort of introduces this scientist Perez, and then in the later part of the text it keeps referring to that scientist. So it is able to use some information which is uh, lying behind. So these were some issues with the natural language generation models before GPT-2, and if you had seen the results, you can clearly spot a lot of grammatical mistakes, coherency failures, and so on. So this was a really amazing result from OpenAI, which really uh, shook the NLP community for some time in trying to see what the model is doing. Yeah. And so it sort of scores well on four metrics at least: coherency, grammaticality, and usage of long-term context and usage of world knowledge to some extent. Yeah. And so we didn't talk about how we would generate such text, and that's where the decoding techniques would come into picture. We would be discussing at least four decoding techniques to generate text, and they are categorized into two categories: deterministic decoding techniques and stochastic decoding techniques. So let's look at deterministic decoding technique. We have two categories, subcategories here: greedy search and beam search. Uh, so we'll look at them one by one. Yeah. So we'll try to look at the intuition for each of these search or now, and then we'll try to code each of these decoding search to generate natural language text. The first one is greedy search. So as the name suggests, we try to predict the next word, and we try to greedily assign the word which has received the highest probability. Right? We are going to be greedy at every time step of our generation, and if you can notice, we have done greedy search already in the neural machine translation course when we were trying to decode the translation in the decoding side, right? So there we always, let's say the teacher forcing was not there, we always looked at the word which has received the highest probability, and we feed that word back to the input, and we try to generate the rest of the translation. So that's exactly what we are going to do here, just that we don't have a separate encoder decoder setting here. It's just an encoder, and we are going to go from there to generate the rest of the um, article. So first we will see an example for greedy search. We will first feed the seed text, the same seed text that we saw previously. Let's say we have the ending now. We feed that to the trained GPT-2 model. The unicorn spoke perfect English, and then we try to see what the model tries to predict, right, as the next word. So that would be a probability distribution over all the tokens in the vocabulary. P of word given the seed text, and we see different probabilities for different words. And in greedy decoding or greedy search, we just take the word which has received the highest probability. So here, let's say this is the probability assigned to the word the, and we are just going to predict the word that as our next token immediately following English, right? And then we can continue the same process. We would append this token the into our input here like this, and we try to predict the next word, and we would get a different probability distribution. We would again try to do argmax and try to predict the try to identify the word which has received the highest probability. Here in this case it is scientist, and yeah, that's our new generated word, and we repeat the process. We append the token again to the input, and we try to predict as much as words as we want, right? So here the partial generation from the seed text is the scientist named the population after, and you can continue this process. So typically we have some number, yeah, like 50 words or 70 words, and we try to stop once we reach the limit that we have. Yeah, so that's how greedy search works, and we would see other searches also. So the other searches vary in the way in which we pick the word from the distribution. In greedy search, we picked the word which has got the highest probability. But there are better ways to do this, and we would see later that just using the highest probable word is not the best approach for this particular setting of natural language generation. We would now move on to another deterministic decoding technique called beam search. I guess Professor discussed beam search very briefly in the neural machine translation course, and this is the most popular technique, decoding technique for neural machine translation. Even the current version of Google's machine translation model uses beam search to generate the translation. Yeah, so we'll see how beam search works. So beam search, as the name says, it uses a beam. Beam is a set of partial subsequences or sequences that we have, and so it keeps track of all the highest scoring sequences, and we try to create new sequences by appending each token in the vocabulary to the existing sequence and try to predict the probability, and then we use that to score. We will this seems very abstract, right? So we will try to look at an example for beam search with beam size as 2. So this is another hyperparameter which we can tweak. Yeah, so we will consider the same seed text. The unicorn spoke perfect English. Let's say we give that to the trained model, and we get a probability distribution over all the words in the vocabulary. Let's say our vocabulary has just 7 tokens, right? These are the 7 tokens, and this is the probability distribution that we have got when we have fed the unicorn spoke perfect English to the model. So different words get different probabilities. After English, the next most likely word could be the, or something, right? Looks like 2 words have got probability 0.6 and 0.2, the and that. And we pick, so in greedy search we just picked the word the and then we moved on. Here we keep track of the best 2 words. Remember, the beam size is 2. Into our beam. So in the beam is a list. It's an ordered list. It's ordered based on the probability of the sequences which are there in the list. We would put the 2 words, the topmost words, in our first time step. The and a, and the is before a because there has a higher probability than a. Right? At any point, the sequence that we are going to generate from beam search is the first item in the list. Okay, so we did the time step 1 now. That seems fairly straightforward, and the slight complication really comes in the second time step. Here we discard all the other words from our previous probability distribution, scientists, named, and population. These were not there in our top 2. We have the 2 words the, na in our beam, and then we use the word the into our input. We append the word the into the input and try to predict a probability distribution. That is the first the topmost table here. And we have another word a, which is the second most highly likely word. We append this word into the input again and try to create another probability distribution, which is the bottommost table here. So we get 2 tables, 2 probability distributions, we get different numbers, and what we essentially do is the same process. So we get a score for each sequence. So this is a score for predicting the word the given, let's say this is the probability for 0.4 is the probability for predicting the word scientist given the seed text and the word the, right? The sequence that we are scoring here is the scientist. The scientist probability is 0.4. And similarly here, when we see the same word, it would be a scientist. A scientist probability is 0.06. So we have scores for different such sequences, and we try to pick the top two, combining these two tables. So you have two tables. You try to look at the top two probabilities from this second column, right? So 0.4, this is topmost, and the second topmost is 0.3. Now uh, we copy these two sequences into our beam, right? Again in ordered manner, the scientist and a researcher. These are the top two sequences or hypotheses we can call. Right. So now we are done with the second step. So at this point, if you want to know what is my generated text, it would be the scientist, which is there in the top of the beam, right? The first item in the beam. Now we'll go to the third time step. It's again the same process. We discard the other sequences which we never put in the beam, the named population, French population, sorry, population, the scientists, every other sequences, we score them out. And then we repeat the same process. Now we have the scientist. Uh, we try to feed that as the input to the model, GPT-2 trained model, and try to see uh, try to estimate the probability distribution that we are getting, right? So that's this, and this bottom table is for a researcher, as the additional input to the seed text that we have. Seed text plus a researcher gives out this probability distribution for us. So these are again two different probability distribution, and we would again pick up the two sequences which are most likely, right? The top two sequences from all these hypotheses based on the probability, conditional probability. Yeah, and we are done with the third time step, and we can do that on and on. And the first item in the beam is always our generated text, final generated text. Yeah. So moving on, people have used beam search to generate natural language text in an open domain setting like what we have. Uh, yeah, and this was done by a recent paper. They tried to compare beam search with a beam size of 32 with pure sampling. So in pure sampling, what happens is you have a probability distribution here. Let's say you have to identify a word. In greedy search, you pick up the most likely word. But in pure sampling, you take this probability distribution over all the words in the vocabulary, and you try to sample from this weighted probability distribution. You find a word, let's say named, maybe the, because the is 60% highly likely to appear in random sampling. Yeah, you can get any word based on this probability. You take that word and then you move on. So pure sampling is very simple, right, in that way. Yeah, compared to beam search. Yeah, so this is the comparison between beam search and pure sampling. As you can see, in beam search, the text quickly becomes very repetitive. Here it introduces some university called UNAM, and it keeps repeating it, and it's sort of becoming degenerate very soon compared to pure sampling. Pure sampling is doing something again, but again it drifted very far from the initial prompt, although it makes it is grammatical and so on, but it's very different from the prompt that we have, right? Yeah. So yeah, so people tend not to use beam search for open-ended generation, like building chatbots and so on. So we won't be covering beam search later in this tutorial. We won't be implementing beam search particularly. We would be trying out other techniques, mostly from stochastic category. The techniques from the next category that we are going to see, stochastic, seems to be the favorite technique which people are trying out to generate reasonable text. So again, in stochastic technique, so pure sampling is one way to stochastically sample. So from a distribution, so we randomly sample and then move on. There are at least two successful techniques: top K sampling and top P sampling. These two sampling methods differ in the way in which they limit the subset of vocabulary to consider. So in pure sampling, we consider all the words in the vocabulary to do the sampling, but we can restrict the vocabulary. Let's say in top K, what we are essentially going to do is restrict our sampling to just the top two words in the vocabulary, the and a, and we try to sample from that, right? So these two methods vary in the way we sample from the distribution. So first let's look at top case sampling. So we have the distribution that we saw already, probabilities for different words given the context. Context, let's say, is just the uh, seed text for our first generation time step. So what we do first for top case sampling is sort all the words based on the probability. Uh, in I guess in decreasing order, yeah, and then you pick the top k words. Here k is 2 in this particular example. The and na is 0.6 and 0.2. You put a softmax to get a probability distribution over the and na alone, right? And you try to randomly sample a word from this particular distribution. Yeah, yeah, that's all top k sampling is. Yeah, and there is nucleus sampling, which is a very recent technique. We call it as a top P sampling also. It restricts the vocabulary in a different way. So it does the same thing. It sorts all the words based on the probability, like this, the second column, and then it tries to compute the cumulative probability, which is the total mass uh, to the highly likely term to the current term. For the is the highly likely term, so the cumulative probability is just 0.6. The cumulative probability for R is cumulative probability for the plus R, which is 0.8. For scientist is the plus R plus scientist, which is this. And if you sum all, the last word gets a probability of 1.0, right? Yeah, that's expected, right? So yeah, and what top P sampling does is it picks up that subset, that small subset of words which satisfies a p value, I mean the probability value of 0.9. So 0.9 is another hyperparameter for this sampling method. This is the only hyperparameter for this sampling method. Um, so the first four words led to 0.91, and these are the minimal set of words which matched this threshold 0.9. And yeah, and again we sample only from these subset of words, the softmax over them, and then we sample from that. Yeah. So we spent quite some time in understanding the background of GPT-2 model and different decoding techniques to generate text. Now we will move on to the implementation. We would perform the following set of tasks in sequence. We would create a toyish GPT-2 configuration by playing with the hyperparameters. We would reduce the number of layers, number of attention heads, and so on to train the model from scratch quickly on help dataset. We would try to load the original GPT-2 model and prompt the model based on three different sampling techniques that we have seen. We won't be doing beam search as it suffers from uh, a repetition problem. We would also see that the greedy search also suffers from a repetition problem and leading to degenerate text. Yeah. So first we would use a help dataset, which contains a lot of help reviews. Just the raw text we would be using for this tutorial. These are the steps for doing it in Colab, which apparently didn't work, so I have commented them out. We will first import the required libraries. We would import certain classes from the transformers library related to GPT-2. Yeah, this line does that. And yeah, we set the seed and all. Here we try to load the default configuration file for GPT-2, which contains a bunch of hyperparameters which were used in the original GPT-2 model. We extract the configuration file, and then we change certain hyperparameters to create the toyish configuration. Namely, we change the number of layers in the transformer model to 2, the embedding size for the word to 60, and the number of heads to be 2. We do that here. Once we change the configuration file, we can pass it to the original model, GPT-2 LM ed model, and instantiate our model. And then we load the tokenizer, GPT-2 based tokenizer. Yeah, from the transformers library. The syntax for importing tokenizer, instantiating the model is very much similar to what we have already done in our bird tutorial, just that the classes are different. We might be using a bird tokenizer in our previous tutorial. Here we are using GPT-2 tokenizer. Yeah. Now we will prepare the help dataset so that we can feed it to our model and train it. So this is extending the dataset class, and we have some functions which we need to define. We will see these functions in some time. Yeah, the train file is sitting here, help academic dataset. You can download it from this URL or the URL above. We set the block size to be 64. This is the maximum length of the input sequence. Yeah. So we instantiate the text dataset, an object from text dataset class. Text dataset takes the tokenizer and the file path, and it reads the help reviews. Each line is a JSON file. So you convert the string to JSON, and then you seek the text attribute or the parameter of the JSON, and you have the raw text. Here in toyish setting, we are just reading 300 reviews, which is extremely little to train any useful model, let alone GPT-2 model. Yeah, so we keep concatenating all the reviews into one single string object, and then we pass the concatenated reviews to the tokenizer. We convert the raw reviews into token IDs, and then we try to create the examples. We move a window of size, block size, which was 64 here, and we create a window and we start appending each window into the examples. So it may so happen that the sequence can span multiple reviews, but if your dataset is really large, this doesn't really make much of a difference. Yeah, so we defined the dataset object, and then we are printing out the number of instances, 690 instances of block size 64 we have created. And then we define the loader To generate batches from our data set. We use the default loaders available in the torch class. We don't go for the torch text, at least in this tutorial. We try to print the first batch or a sample batch from the training data set. The batch size is 2, so a single batch, the tensor of a single batch has a dimension which is 2 cross 64. 2 is number of sequences and 64 is the sequence length. And these are the other hyperparameters for our training. The batch size 50, the number of training steps 25. We have other hyperparameters. Here we create the iterator for creating batches from the training set. Here we say give a proper batch size which is 50. Yeah. And then here we define the optimizer for our model. We define two optimizers, uh, one for all the bias terms, uh, and the other for the layer norm term. Let me just check. Yeah, you don't need any sort of weight decay. Oh no, yeah. So there are two configurations. So the first optimizer is for weights in the model, which requires decay. The second is for weights in the model, which doesn't require decay. So the components such as bias and the layer norm, which is again a transformer component, doesn't require any decay. So we define such an optimizer. We use Adam and we use a scheduler. Yeah, I think scheduler I guess helps in the training process later on that we'll see now. So this is the old training code, which is a typical code for training a neural net. You have certain bookkeeping variables, and you uh, have the iterator, and then you run over the iterator, and then you then run over the trained data here, and you extract uh, a batch of sequences, and you feed the input to the model. So if you see, the input and the labels are all the same, right? But if you think the label should be shifted uh, to the right by one, right? So internally, the transformers code takes care of this shifting by one, so we don't really need to do. We can simply pass the inputs as such as labels like this, and we get the loss, and we can keep accumulating our loss. We do a backward to do the back prop. We look for large uh, gradients, and we try to clip them so that we take care of the gradient explosion problem, and then we make the update, and we keep track of the number of global steps that we are making, and we know when to close. Yeah. Did we use the scheduler? I guess we didn't use it. We did use to update the learning rate schedule. Okay, yeah. So this scheduler takes care of well, managing the dynamic learning rate for different components in the model. Yeah, and so this is the training. I mean, it's extremely quick because we are only training on 300 help reviews. is just for uh, getting a feel of how to train a language model. But training it on a large data set like web text or 1 million benchmark or Wikipedia would take considerable amount of time, would require a lot of code optimization, which we are not dealing with in this tutorial at least. Yeah. So now we'll move on to the generation part. So far we have trained a GPT-2 model on a toy dataset. Now we are interested in generating something from a GPT-2 model. Yeah, so for that we need a seed text which we can give as input to the model and expect some generation from the model. So the seed text that we would be using is exactly the one that we saw in the image earlier in this tutorial. That seed text about unicorns, and I have added one extra word there. Otherwise, it's roughly the same. Yeah. Hmm. And we would be using the original GPT-2 model, which is pre-trained on web text for generation. We won't be using the toy model which we have generated. We know the large model requires tons of data to train adequately, and we have just 300 reviews, and still it's not enough to make anything useful out of a language model. uh, yeah, sorry for that. Yeah, so where were we? Yeah, so now we are in the process of loading the original GPT-2 model, and they came in different sizes. We are going to make use of the smallest model, which has 12 layers, uh, 12 layers, and then different number of heads, which is extremely limited compared to the large model, which had about 40 plus layers, or something. You can look into these details in Hugging Face pre-trained models link. Yeah, and we load the tokenizer. We set the eval mode because we are not really going to update the model weights. We are just going to make inference. And we set the number of words that we want to generate. It is 670. Now we will start exploring one decoding technique at a time. The first one is greedy search. We have the seed text. We try to tokenize the raw seed text into token IDs. So we use the tokenizer. We convert that. So as you can see, I have printed some of the token IDs coming from the seed text and the corresponding raw version of those IDs here. So there are totally 53 tokens from the seed text that we have seen. And we convert these token IDs, which are in raw Python list form, to tensor, so that we can feed it to the model. We do that here, torch.tensor the seed tokens. Yeah, and the size of it is 1 by 553. Right, 1 is the number of sequences. For us, we have just one seed text, and that seed text has 53 tokens in it. Yeah. Now we will feed the seed text, uh, prepare it in this form by putting it in a map and feeding it to the model which we loaded before, and then we uh, try to plot the size of the output. It's 1 times 53, 1 by 53 by 50257. 1 is the batch size, which is 1 in our case. 53 is the number of tokens in the seed text, and 50k ish is the number of tokens in the GPT-2 vocabulary, right? Yeah. So we have the so this outputs is the sequence of hidden states at the last layer of the GPT-2 model. Uh, uh, so it's actually the probability distribution after the hidden state. So it's not the sequence of hidden states; it's the sequence of uh, output token output probability distribution for each token. And yeah, and we would be interested in the probability distribution coming from the last token, the 53rd token. So we would want to know the next word right after the. So we would seek the last word probability distribution here, and that's next token logits. Yeah, so that's unnormalized. That's before softmax. And now we would try to see how to do greedy sampling, right? We have seen this picture already in the tutorial. We try to get the probability distribution for the next word, and we pick the word which has received the highest probability as the next word to be predicted. So in this case, this word the has the highest probability, and we would predict that as the next word to be generated. So that's exactly what we are going to implement here. We are going to use the argmax function for the with the next token logits, which contains the unnormalized probabilities, and it gives you the token ID which has received the highest probability. And that token ID is 4837. I have no idea what that token refers to. Let's look at it here, right? I am trying to print the generated text so far in ID's form here, and then what we can typically do to go ahead and finding out the next token is to concatenate this next token into the generated, and we can do the same process again and again, right? We can concatenate this append this token to the input and try to predict the next word, and then you append that predicted word again to the input, and you keep repeating the process until you have reached the number of words that you want, right? So yeah, here in this case I am printing the generated token IDs after I do the concatenation. I append 4837 so that it's this generated torch tensor can be directly used as an input for generating next word. And now I'm trying to print the raw form of the seed text plus the generated text. So far we have generated just one word. Let's look at what that word is. So this was our seed text until this point, and the word that we have generated just now is researchers, the token corresponding to the ID 4837. Yeah, we can keep repeating this process until we have reached the maximum number of words. And this is the full-fledged code which arranges all the previous codes that we have seen for greedy search. So the code starts from here. We have the seed text which is here, and then we call the greedy search function. Greedy search function would convert the raw tokens into IDs, and then this step converts the IDs into tensor, and then we feed the tensor to the model, and we get the next token logits, and then we do argmax to find the word which has received the highest probability, and then we attach that token into the generated original tensor, and we keep looping this process. Once we have reached the maximum number of nodes, number of words that we need to generate, we then call decode function from the tokenizer to get the raw text. Yeah. So the raw text that we have generated through this process is the following. Uh, yeah. So yeah, so this is our seed text till the, and the continuation is this. Researchers say that the unicorns were able to communicate with each other through their speech, communicate with each other through their eyes, and then it keeps repeating, right? The pattern seems repetitive here. Through their eyes, there is no real diversity in this text, and it's mostly meaning less, right? So this is the core problem of greedy search. I think we saw such a problem with beam search also. So people don't really use deterministic decoding techniques when it comes to open-ended natural language generation. So we try to solve these problems typically by resorting to uh, sampling based or stochastic decoding techniques like top K and top P. We'll look at the top K sampling now. We go through the same process. I don't really want to repeat the process of converting the seed text into the token IDs. We do that here, and then we convert. The steps are pretty much repetitive. The only change which comes is when you get the next token logits, and now you need to decide which word I'm going to output. So since I'm using top K sampling here, and we have seen this theory already, we sort the words based on the probability and then take the top two words. In this case is the and a, and then we put a softmax, and then we try to predict a sample a word from that probability distribution randomly, right? Yeah, based on this weighted distribution. Yeah, so that's exactly what we are going to do. Instead of using argmax that we did in greedy search, we are first calling the top k function from the next logits, and the k that we are using is 40. I think this is the default decoding technique of GPT-2 model originally. The authors used top k sampling with a value of 40. So the first thing that we do here is to remove all the tokens with a probability less than the last token of the top k list. So in this particular example, we want to remove all these tokens: scientist, French, researcher, population, named, uh, mainly because they are not in the top k, and they are lesser than the last word in the top k. The last word in the top k is a, and yeah, we want to remove these words. So this indices to remove would contain true for all these words in this example and false for the na. Once we do that, the next thing that we do is to change the probabilities for these words that we want to remove. So for these words, we would substitute a negative infinity as the probability. Exactly this. So what it does is, when we sample from this probability distribution, the word would most likely be picked from the top two words, and would never be picked from would only be picked from the top two words, and would never be picked from the other words, which has negative infinity as a probability. So that's exactly what we do. So we call torch.multinomial, which does this sampling from a weighted discrete distribution. So we do the softmax over the next token logits, and by default, for the words which has a negative infinity as probability, would never be sampled. And so we have sampled a token from this distribution, which is 717. And yeah, so the text and the next set of commands are pretty much repetitive, and we can look at the word that we have generated, which is 717, and that means first. Yeah, and we can repeat the same process again and again to generate subsequent words. And this is the full-fledged code for top k sampling. Pretty much the same. The only change which happens is in is in this part. Yeah. So we ensure the top K is minimum of the number of words in the vocabulary, and the top K, the user shouldn't be putting a top K which is greater than the vocabulary. If it is so, then the top K has to be a minimum, right, of the user input and the actual number of tokens in the vocabulary. That's taken care here. Doesn't really generally happen. And then we have these two commands that we talked about. We mark the words which we need to remove, and then substitute a filter value which is negative infinity for those words, and then use the multinomial function to sample a word from the distribution, and then we keep doing the process. And let's look at the generated text through top case sampling. Yeah, the only explanation for this is that unicorns have learned what many people will most likely never know. The language is a sign. It talks about the language which we entered here by talking about perfect English. Seem like people living in the valley. Maybe it is talking about the Andes. Oh no, the Andes mountain, the valley in the Andes mountain. And yeah, so it takes care of the aspects that we have mentioned in our seed text. So it's mostly, interesting, not really repetitive like beam search or top beam search or um, greedy search. And it's mostly making sense, right? Yeah. So yeah, so this is the default configuration. Top K has 40 used by the GPT-2 authors. We also have one more sampling, which is a very recent sampling method called nucleus sampling. We have seen this, seen the theory before. We do the same thing of converting seed text to token IDs and then pass the token IDs to tensor and then pass the tensor to the model, and then we extract the next token logits from the probability distribution for the last word. And now we need to do top P sampling. So we saw the theory before. We have a probability distribution like this. We sort all the words based on the probability, and then we pick the minimal set of words which whose total mass is greater than the threshold that user has given. So the threshold is 0.9. So the minimum set of words which meets this threshold can be obtained by sorting the words based on the probability, and then keeping track of the cumulative probability, right? So cumulative probability for the is just 0.6, for A is 0.6 plus 0.2, and scientist is 0.6 plus 0.2 plus 0.06, and you keep accumulating, right? And then you reach a point where you exceed the threshold, and that's where you stop, and these are the words that you need to take into account for top P sampling. The sampling process is pretty much the same. Once you get the subset of tokens that you want, you put a softmax and then you try to sample from this discrete distribution, right? Weighted discrete distribution. So we'll implement these steps through code. First thing we do is sort the next tokens in a descending order, and then we do that here, and then we try to compute the cumulative probability, this particular column. We do that here. The size of that is 1 cross number of words in the vocabulary. In our example, we had just 7 words. And then we try to mark those words that we need to remove. So we try to remove those words whose cumulative probability is greater than 0.9. So for this example, we remove all those words whose cumulative probability is greater than 0.9. So that means we include the French word also. We'll get there. French, researcher, population, and name. For now, we remove that, let's say, right? And but we need to keep track of the first word, right? This word, French word, which first word which is above the threshold. So 0.91, this is above the threshold. We are going to keep that, right? That is uh, subset. So that's the change that we are going to make here. So we are right shifting the indices by one. So yeah, so that we are doing, and then we are making the first word as a word that we don't need to remove. So what we are doing is, if we would have false, 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 true, 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 three false plus four trues initially, telling you that French word has to be removed, and then you right shift this array of trues and false by one, so that and so that you have false, 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 false. You don't want to remove this, and then true, true, true. You ensure that the first empty value is 0. It's false. You don't need to remove these four words. So that's exactly what you do here. You right shift everything by one, so that you have this extra token which is above the threshold also into the tokens which you don't need to remove. Yeah, so that's exactly you do here. And then these are sorted indices IDs. So the original indices are this 1, 2, 3, 4, 5, 6, 7, and the sorted IDs are this. Probably the original to sorted IDs need not be same in most cases. So we map the sorted IDs to the original IDs, and then we substitute negative infinity to the words that we don't want to sample. Pretty much what we did in top K sampling. And yeah, and then the rest of the process is same. We try to use multinomial and we try to sample a word, and we have sample 7185 token. Let's see what that word is, right? It is creature. Yeah, sounds interesting. Yeah, and then the code is roughly the same, full-fledged code for top P sampling. The only change is the set of commands that we discussed before, and yeah, otherwise the code is roughly the same as top K sampling. Yeah, and we'll see the text. Unicorns did not give birth to male sons. They took on a different and more apparently homosexual type of behavior, and they are not. They are still making sense, but they seem to be talking about unicorns again, which is good. Uh, which is good. Uh, yeah. Yeah, so but then again, it is talking only one aspect of the unicorn. It's not really talking about the language aspect, but it's a fair balance still. Fair balance of adhering to the prompt and then being consistent and all. Yeah, so that's top P sampling. I mean, the authors who have proposed top P sampling have argued that top P sampling is better than top K sampling, in that it gives you a dynamic subset of words for each sampling. And then they argue that this dynamic subset selection matches the confidence that the model has for each word. That really helps. So in top K sampling, we add a fixed number of tokens which we would sample from. So that might be either be overestimate or underestimate for several number of cases, and then we start sampling from some really low confidence tokens, and then the generation gets missed. So it's a lot theoretical, theoretical difference on the difference between top P and top K sampling. But I guess, yeah, if you are more interested, you can read the fourth reference to understand why top P sampling really works. Yeah, so that's it. And if you are really curious about GPT-2 or natural language generation in general, you can open this link It is from Hugging Face, uh, which owns the Transformers library, and you can basically generate you can basically type and then ask a transformer to fill the rest, right? So you can I can just do this. Again, autocomplete. Let's see what is the next word. A brief. Let's see a brief example of how to use. Yeah, it seems use the transformer, right? Cool. We have the knobs that we can play with. GPT-2 large. We were using GPT-2 small, and then different values for the hyperparameters. Top P sampling hyperparameter, and temperature is another variable in the softmax function. I mean that also controls the probability that you assign for the low probability tokens. We haven't really discussed that, but that is also one potential way to stochastically sample from a probability distribution. I Yeah, I guess that's all. uh, Thank you.